In the figure, we see two vectors, A and B, that have an angle alpha between them. We'll define here the dot product of A and B, which is defined as A dotted with B, or A dot B, is equal to the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. The dot product is also called the scalar product because the value is a scalar. You have two vectors going in, and what you're getting out is a number, an amount. This dot product is used to help project one vector into the direction of another vector. And so this scalar amount is a measure of how much the vectors are aligned. Thus, when you look at the value of a dot product, you are looking at how parallel two vectors are, or how aligned they are. If the dot product is positive and is fairly close to the value of A dot B, that means that they are pretty well aligned, they are mostly parallel. If the value of the dot product is close to 0, that means that the vectors are not very parallel, that they're mostly perpendicular. And if the dot product is a large negative number, that means that they are parallel, but in fact they are anti-parallel, they're pointed in opposite directions. We see some different cases here. When the angle between the two vectors is 0, those angles are perfectly parallel. In that case, the dot product is just the product of their two magnitudes. If the vectors are close to the same direction, but there is an angle between them, then the dot product is greater than 0. It's not as big as the product of their two magnitudes, but it is close to that, relatively speaking. What the dot product helps us find is the magnitude of A projected into the direction of B, basically how much of this vector A is in the direction of B, or conversely, it can be used to help us find how much of angle B, or vector B, how much of vector B is in the direction of vector A. If the two vectors are fully 90 degrees apart, if they're fully perpendicular, then their dot product is 0. Recall the dot product is a measure of how parallel they are. If they're perpendicular, then they are 0 parallel. If the angle between them is greater than 90 degrees, then that means that they're closer to anti-parallel. They're pointing in opposite directions, and thus their dot product is less than 0. It's a negative amount. And if the angle between them is fully 180 degrees, if they're fully on a line but opposite directions, then they're anti-parallel, and their dot product is the negation of the product of their magnitudes. We've seen how you can find the dot product of two vectors using magnitudes and angles of those vectors, but you can also find the dot product using the components of the vectors themselves. In that case, the dot product of two vectors is the sum of the products of each set of components. So you multiply the x components together, plus you multiply the y components together, and then plus you can multiply the z components together as necessary. To visualize that, we can imagine two vectors, and we can pick them to be in any direction that we want. We'll just pick first and second quadrant. And so in this case, we have vector A. Vector A has an angle theta, and vector A has a y component and an x component. When we look at vector B has an angle phi. It has a y component and an x component as well. And when we try to combine these values, basically we're saying that the dot product of A dotted with B should be the magnitude of A times the magnitude of B times the cosine of the angle between the two. Here, this angle between the two, alpha, could be written as phi minus theta. Whatever those two angles happen to be, whatever angle phi is and whatever angle theta is, alpha, the angle relative to the two vectors, is phi minus theta. What we can do then is use one of our angle addition formulas here to say that cosine of phi minus theta is cosine of phi cosine of theta minus, plus sine of phi and sine of theta. That this term here equals that. That's one of our angle addition, angle subtraction trig identities. If we distribute our AB and if we reposition the values, because multiplication is commutative, it doesn't matter what order we do it in, we can distribute and get this. And what we have here, A cosine phi is the x component of A. B cosine theta is the x component of B. A sine phi is the y component of A. B sine theta is the y component of B. And thus we see that the dot product must be the sum of the products of the vector components. We never said what the magnitudes A or B are. We never said what the values of the angles are. If these angles, theta or phi, are in different quadrants, then the cosine or the sine would give us plus or negative values, which would give us plus or negative values for these components as well. Thus, we can return to what we saw before, where we have an object, a particle, that's moving along some direction S, and we have some displacement along this arbitrary direction. And we have a force that's acting on the particle that's partly in that direction of motion and partly perpendicular to that direction of motion. And what we see is that that only the component of the force parallel to that motion is contributing to the work done. And we said before that we have to take the force times cosine theta to project the force into the direction of the displacement. What we see now is that in fact what we're doing is taking the dot product of the force and the displacement, and that is what our work is equal to. This dot product does the work of projecting our force into the direction of our displacement. It's looking at how much they are aligned, and however much they are aligned, that's the amount of work that's done. The amount of force that's not aligned with the displacement doesn't contribute to the work.